Good morning or good afternoon to eighth period. Welcome back to school on this fabulous Monday. Um, my kids have finished debating. I don't know how they did because I actually recorded this on Wednesday. So let's hope for the best that they got into the final eight and hopefully maybe even got better than that. But what we're going to review today are some radical rules. You might have covered this in Algebra 1, you might have not. Who knows? Some of us did not go here and have Ms. Petru. So I really don't know what we did last year in your math class. So radicals, that's the word for this little shape right here. We often call it just a square root because if we don't see a number, we can assume that the number on the outside is 2. There are some special vocab words for this. And it gets a bit technical. So I just wanted to review that real quick. We often don't use them at all. So the shape itself, again, this is the radical, the number inside of this, and we're going to start off talking about 18. That is called the radicand. Radicand. We don't actually pronounce the last D. This number right here, the 2, is called the index. Again, some of these words we use sometimes. It just helps us clarify stuff when we're talking. So as I said, we're going to start off talking about if the radicand is 18. If we plug that into the calculator, we'll get some messy number. We want to keep this simplified exact, which means no decimals. It unfortunately means we have to do a little bit of work. There are 2 ways to do this. We can do it the way where we try to find squares that are factors of 18. So we need to think of the most common squares that we know. We know 1 is a square, but it's not helpful. 4 is a perfect square. 9, 16, 25, 36, 49, 64, 81, and 100. That's usually all the ones that we're going to be looking for. Sometimes we use bigger ones, though. So we can use this method. So if we do that, we're looking for any of these numbers that are a factor of 18. Some of you have probably said it out loud to yourself already. 18 is also 2 times 9, which means we can actually break this up as the square root of 2 times the square root of 9. We know what the square root of 9 is, and that's 2 times 3. And we rearrange this so the number comes first and then the radical. So the simplified version of square root 18 would be 3 times the square root of 2. If we plugged both of these into the calculator, we would get the same decimal. But this is the pretty form of the square root of 18. It is simplified. It is exact. So just like when we're talking about fractions, 1/3 is exact, 0.333 is approximate. This is the exact version. The other way to do this is to find all factors. So this is often what we did with a factor tree. So it doesn't matter what order you do it in. We can do 18. I know that's 6 times 3. 3 is prime. I'm going to circle that. I'm going to break 6 down further into 2 and 3. So when I rewrite this, the square root of 18 is the same thing as 2 times 3 times 3. The square root is asking what number times itself will give us that. So we're looking for pairs of numbers. So find all factors and look for pairs. So that means if we have a pair, we can take it out of the radical. And when we take it out, it loses its partner. So we have 3 times the square root of 2. 2 didn't have a buddy, so it can't come out. We get the same answer, just different ways to think about it. Either way you do it is fine. So we're going to do one more example here. All right, let's find the square root of 700. I'll do it both ways. So let's do all the factors first. So we have to break this down. 700, probably first thing is 7 times 100. 7 is prime, but 100 is not. We can do 50 times 2. Doesn't matter how we do it, just the first pair of factors that come to you, choose it. So 2 times 25. And then lastly, 25 is 5 times 5. So 700 is the same thing as if we did 2 times 2 times 5 times 5 times 7. I'm looking for pairs of numbers here. So there's a pair of 2s that can come out. There's a pair of 5s that can come out. The 7's all alone, so it can't. So this turns into 2 times 5 times the square root of 7. 2 times 5, we can do that, so we get 10 times the square root of 7. That's our first way of doing it. We could have also done the method where we look for squares. I look at 700, something that could come out right away is that we can do 100 times 7 to get to 700. We know the square root of 100. We do not know the square root of 7. The square root of 100 is 10. The square root of 7 stays itself. So sometimes one way is faster than the other. Sometimes it's not. Just kind of have to roll with it, figure out what you find the best way to do it for you, and stick to that. All right, so that's simplifying. That means taking the radicand and trying to make it as small as possible. So making radicand as small as possible. All right, next up, multiplying. So that means if we have something like this, the square root of 5 times the square root of 10. What does that mean? We can plug in our calculator and see, or we can try to keep it exact. So when we have this, two radicals multiplying by each other, we can actually just multiply the two radicands together. So we can get the square root of 50. We're not done yet though. We always need to simplify. So we look at the square root of 50. Can anything come out of that? I can break that into 2 times 5 times 5. I have that pair of 5s, so it'll be 5 times the square root of 2. Let's try this again. Let's do something like the square root of 6 times the square root of 33. Odd numbers, let's see what we get. We multiply that together. We can do that by doing 6 times 33. I don't actually like doing this step right here. I'm going to break this all apart first because I know my end game is to simplify it anyway. So 6 is the same thing as 2 times 3. 33 is the same thing as 3 times 11. So I'm going to get to this point anyways. I really don't need to know what 6 times 33 is. I can factor those numbers right away. I see a pair of numbers, so they can come out, but they come out just as 1, 3. We have 2 times 11 on the inside, so we just do that real quick to get 3 times the square root of 22. So if we plugged in any step of this work into the calculator, we should get the same thing all the way along. We're not changing anything. We're just changing how it looks. We're putting a new outfit on it, or we're making it strike a different pose. It's not changing its value. The other type of problem you're going to get is something that looks like this. 2 times the square root of 10. We're going to actually multiply that by another kind of mixed number like that. Let's multiply it by 7 times the square root of 15. So when we have this, we're going to multiply like numbers with like numbers. So here 2 and 7 are both whole numbers, so we can multiply those right away. And then we can combine the two radicals. So we have 10 times 15. Again, I really don't care what that is. I'm going to break them apart. So we have 2 times 5 times 3 times 5. I look at that, I'm thinking, are there any pairs? We have 5 and 5, so they can come out. So we have 14, whole number on the outside, times 5, which is the number we could take out, times the square root of the two things that we could not take out. So 14 times 5 is 70. 2 times 3 is 6. So that's our final answer. So that's multiplying. Multiply like numbers by like, whole numbers, multiply by whole numbers, radicans by radicans, and then try to simplify after that. The next one real quick is dividing. So this is where things get a little tricky. We have division. So just like multiplication, if we had the square root of 10 and the square root of 5, we can actually combine that into one big radical, into 10 over 5 inside the radical, which just simplifies to the square root of 2. We can't simplify that. 2 is as small as it's going to get. There's nothing else to do, right? So that's our first step. Whenever we see a fraction bar, we should always see if we combine into one big radical, will it make things simpler? If we had something like this, the square root of 3 divided by the square root of 21, if we combine this together, we get 3 over 21, which we can simplify that fraction, but it doesn't really make it more simple. We could break it apart again, have square root 1, square root 7, so we have 1 over the square root of 7. That is simplified technically, but it's not the easiest type of division to do because there's actually one more step we would need to take with that. But that's one way to do it. We could also do this same problem, square root 3 over the square root of 21, by actually splitting it up into its factors. So 21 is the same thing as 3 times 7, which we can separate like we learned upstairs in the multiplying. We have the square root of 3 times the square root of 7. These cancel out, so we're left right away with just the square root of 7. So sometimes you have to play around and see, build up that gut instinct of which way would be best. Let's look at one more example of this. Let's do the square root of 24 over the square root of 15. When you look at this, if we tried to combine that into one big radical, probably wouldn't make things too easy. So let's actually do the method where we break it up into all of its factors. So 24 would be 2 times 12. 12 we can break down into 2 times 6. And 6 is 2 times 3. So those are all the factors of 24. 15 is just 3 times 5. So we can rewrite that as all the separate square roots. And we do have something here that cancels out, the 3 on the top and the 3 on the bottom. So on top now we have the square root of 2 times 2 times 2 over the square root of 5. But we notice here how we have a pair 2 at least. So we can take that out. One of the 2 is left behind. Square root 5 on the bottom. So this is as simplified as we can get with what we know already. There's one more step we need to talk about, which is called rationalizing the denominator. Basically what that says is we do not like radicals in the denominator. Someone decided on that. We want to get all of our radicals out of the bottom of the fraction. We only have one way of doing that, and it's called rationalizing the denominator. So we're going to take the answer from our last problem. We have 2 times the square root of 2, all divided by the square root of 5. The magic way, not really magic, the magical way that we get the square root of 5 out of the bottom is actually multiplying this fraction by 1, because we know when we multiply by 1, it doesn't change anything. Except we can make that 1 look like something else. We can turn it into a radical over a radical that's still equal to 1, but once we multiply these two fractions together, get the number on the bottom to be no longer a radical. It's a very surefire way, very quick. We always multiply by the radical that's on the bottom. What I mean by that is here, the square root of 5 is on the bottom, so we're going to multiply the fraction by the square root of 5 over the square root of 5. What's going to happen is we have 2 times 5 here now. On the bottom, we have 5 times 5 inside the square roots. We have this pair of 5s, which means it can come out. So we have 2 times the square root of 10 over 5. Still a fraction, nothing we can do about that, but at least we have no radicals on the bottom. Sometimes, what's fun is that when we do this, things clean up and actually look better since we rationalize the denominator. An example of this would be this messy looking fraction. We have 6 times the square root of 5 being divided by the square root of 3. We don't like that radical on the bottom, so what do we multiply it by? Hopefully you all answered me. We multiply it by the square root of 3 over the square root of 3. So what's going to happen is we have 6 times the square root of 5 times 3 divided by the square root of 3 times 3. Because the way we did this, we always get the bottom to be able to be simplified. So we get 6 times the square root of 15 over 3. But look at that. 6 and 3 can be reduced into just 2. So we get 2 times the square root of 15. That's our final answer. If we actually check this in our calculator, and we're going to do this on my phone, so give me a second to prove to you that these are the same thing. If we do 6 times the square root of 5 divided by the square root of 3, we get approximately 7.746. If we do 2 times the square root of 15, we still get 7.746. So although these two fractions, these two numbers look extremely different, as their decimal versions of themselves, they are exactly the same thing. Let's do one more example. Let's do something a little bit more complex. Let's do 10 times the square root of 27 divided by 6 times the square root of let's just do 5. So when we look at this, might not be much we can do, but let's try it. We have the radical that's on the bottom. That's the one we want to get rid of. So that's the one that we multiply by. So we have the square root of 5 on both the top and the bottom. So when we do this, we get 10 times the square root of 27 times 5 divided by 6 times the square root of 5 times 5, which means on the bottom we just get 6 times 5 because these 5s form a pair and can come out. On the top, we have 27 times 5. Again, just as we learned above in the multiplication, that's not something that I actually care what it is. I want to know what 27 breaks down into. 27 is 3 times 9, and 9 is 3 times 3. So here are all the factors of 27 times 5. Again, notice how we have a pair of numbers that come out. So now we have 30 times the square root. We have these two numbers left over, so that's 15 over 6 times 5, which is 30. Look how nice that cleaned up. We have a 30 on the top and the bottom. So that whole nasty fraction is cleaned up into a nice final answer, which is just the square root of 15. So this is maybe what you've seen on some PSATs where it says simplify the radical, or there's some work like this. I'm just going to give you practice for the rest of the day of trying to simplify radicals, multiply them, divide them. If we ever have a radical on the bottom of the fraction, you need to